Okay, so I was debating having you guys read this section out of the textbook, and it's got a lot of information, and I think I can do it a little bit better with simplifying it. So we're doing a lot of upfront. We got about 3 slides of a lot of information, and then we're going to come back together and kind of pull through this information, do some practice problems, see how the math actually works out in it, because it is quite a bit that we have to kind of get up front before we can even do anything with it. So talking about energy. Now, there's 2 different types of total energies we can talk about when we're talking about objects in motion. There's just general total energy, and then we have total mechanical energy. So what we've been talking about so far has been kinetic and potential. That's just mechanical, and I think I'm going to have that down later. But when we have total energy, there are other energies besides kinetic and potential. The total energy of a system also includes internal energy, usually heat, but this can be chemical as well if we're talking about something involving chemical properties, a chemical reaction, that can be included. So, for example, when we have an object sliding across a rough surface, what's going to end up happening here is that friction is going to cause some of that kinetic energy of that motion to convert to heat energy. So this is a form of internal energy. And when objects collide, the same thing happens. If you have a car crash and 2 cars collide, that actually generates a lot of heat. Part of obviously why the cars bend is because they're colliding, but actually a little bit of heat goes into making the cars easier to mold, right? That collision causes that heat, which is also going to cause the car to crumple. So when we're talking about total energy, we have to understand that there might be a situation where it's not just kinetic and potential. Again, if we have friction going on, you guys know this because you do it when you're cold, right? You rub your hands together and your hands get hot, right? Some of that energy I'm generating is being dissipated into heat. So again, total energy includes that as well. Typically it's heat they're talking about, but like I said, it can sometimes be other types like chemical energy. Now, we talked about the work energy theorem for just a single object, right? Which was that work net equals the change in kinetic energy. Kinetic final minus kinetic initial, yeah? That was back before fall break. Now, when we're talking about a system now, a system is when we have situations with potential energy, because you can only have potential energy if we're talking about the forces between 2 things. Yes, if I have a ball dropping, it's going to have potential energy because that gravity has the potential to increase its kinetic energy. But if I have a car driving, yeah, we don't necessarily have potential energy in that case if I'm just focusing on the car, because it's just going, right? It's just the engine is just going and pushing it. It doesn't really have any more potential necessarily in the same sense as a ball dropping. Yes, that potential energy is going to increase the kinetic energy later. If I just have a car kind of driving along, especially at a constant velocity, the kinetic energy doesn't have any potential to increase. So when we have gravity acting on something, we have a lot of potential for the kinetic energy to increase. So this is a different version of the work energy theorem. When we're talking about a system, typically, again, it means when we have a situation with potential energy. So this is that the work done in this system is the change in kinetic energy plus the change in potential. I'm writing it as U because that's the way it's in the textbook. Just be aware that can interchange. They use U sometimes for potential energy. Sometimes they say PE. Yeah, it kind of goes back and forth. As well as the internal energy. So again, sometimes we are going to have situations where heat is going to dissipate a chemical reaction occurs that initially was just being held kind of inside the system until we had that reaction. So we need to include this concept of internal energy, which again, we're going to learn a little bit later, really just means energy that can be dissipated. We'll talk about that later. So just be careful here. Whenever they're talking about mechanical energy, that's energy only related to its motion. And that's literally just kinetic plus potential. That's it. If we're talking total energy, we have to take into account the possibility that there's other energy that might end up being dissipated. Total mechanical energy is just kinetic and potential. So with that in mind, we have to talk about what it means when they're talking about conservative versus non-conservative forces. So conservative forces stay in the system. From the start to the end of the motion, all the forces and all of the energy, and more importantly, all of the energy kind of caused by those forces stay in the system from beginning to end. It's the exact same. Whereas non-conservative forces dissipate. So this is again like heat, right? Heat just goes away. Yeah, I rub my hands together and then eventually we can feel that heat leave our hands, right? Now, think about it like this as well. Think of just if I'm tossing a book. So I'm tossing a book up and down. Yeah, or a notebook. It's kind of hard to catch it if it's a big book. Now, if we only look at the book earth system, what that means is I'm taking my hand out of the equation. I'm pretending this book is literally going up and down, like magically, like a ghost is doing it, yeah? We are only looking at the book as it starts and ends motion, independent of the cause. So again, we're pretending this book is just like lifting up and coming back down. So in this case, the total energy is just kinetic plus potential. It's just the motion of the book coming up and down due to gravity. There's no other forces acting on it. If we ignore that my hand was what caused the book to lift, yeah? So if I'm looking at just that system, total energy is your kinetic plus your potential. However, when you include your hand in the equation, now we have the work energy theorem. Because it's not just the book going up and down due to gravity. Now it's the book going up and down due to gravity and your hand as well. That's more than one thing, yeah? So this now is going to include in all of that system, yeah? The book, gravity acting on it, and my hand acting on it. I'm going to have some internal energy expended that is not going to be conservative. You had to expend internal energy, right? I can't just toss up a book up and down for the entire day. Eventually, my arm would get really tired. If I kept doing this, it might be a form of torture. Who knows? Someone just made me do this over and over again. I'm going to get tired, yeah? I have to expend energy to do that. So when we include you in the equation, you have to consider, well, in order to do that, I had to actually use some of my internal energy, and I am included in the equation now. So this would be the energy right here that I expended in order to get this book moving. The total energy, yes, includes the kinetic and potential of the book, but also now, since we're including me in the equation, the energy I had to expend. Now again, this is a non-conservative force because that energy I had to expend, it doesn't just magically come back to my hand when the book comes back down, right? It's not like, oh, there's a lot of energy and now the book is back and like, hey, I could do this all day. Yeah, I lose a little bit of energy when I toss the book up, but once the book hits my hand, hey, magically that energy has returned. No, that would be really cool because we could probably work all day long and not get tired. That would be awesome. But that energy is non-conservative. Once you push the book up out of the air, that energy is gone. It has dissipated. It has dissipated in the form of heat in your muscles and chemical reactions inside you that you used in order to get that book moving. So again, we have to be very careful when we're trying to see what is included in our system. If it's just the motion of a single object, that's just kinetic plus potential. If they are talking about a situation where there are non-conservative forces, forces that just dissipate and don't come back, we have to consider that addition as well. Now, when you have a frictional interaction between a surface and an object, so again, this is like my hands, I don't have more than two hands, rubbing together. This is also considered non-conservative, like I just said, because it generates heat, which is a form of dissipated energy. But this, again, is for anything. Yes, we can feel it when we rub our hands together because it's our hands, right? But even as I slide, for example, if this were a surface, even as I slide my phone across a surface, heat is generated. It's very, very small. Doing just that is not going to cause like my phone to melt, right? But if I rubbed hard enough, probably, and on a rough enough surface, we would actually feel heat being generated there. So any situation where there is friction involved, we are going to have some internal energy being released in the form of heat. Now, in this case, the internal energy that ends up being taken from the system, because again, if there was no friction, if this was an ice block, zero friction, if I just slide my phone across it, that just had kinetic energy, and it's going to be the exact same kinetic energy the whole way out, it's totally fine. But if there's friction involved, that's going to change my velocity, and that's going to, again, be impacting the total energy of the system. That friction is going to slow my object down. It's going to impact the energy. So we think about it kind of as the energy being taken from the system, which is why we call it negative energy internal. And again, that always read that to yourself. It's not negative triangle, right? It's negative change in energy. So where was the energy internal that I started with to the energy that I ended up with? And again, that's going to go away like the heat dissipates. And so we call it negative. Now, what this ends up equaling is the work done by any non-conservative force. And we know that work is force times distance. So in the case of friction, the energy that we lose is equal to the force of friction times the distance. Again, really, the work done by friction is the energy that we lose. If there was no friction, we wouldn't lose any energy. Again, you know this. If there was no friction and I pushed my phone, it's gone. It's lost forever. It's going to continue on until some other force acts upon it. But if there is friction, again, energy is going to be taken from that system, slow my phone down, and eventually cause it to come to a stop. So once more, what this means here. The energy a system loses when there's friction is equal to the work done by that friction, force times distance. That's what that means. Again, I know this is a lot right now, but like I said, I just really kind of wanted to front load you. And then as we go through the problems together for the rest of class, you'll have these to refer to, and I'll kind of pull these notes back up so we can kind of pick them apart. We got one more slide. We're going to look at them. So once more, talking about total mechanical energy. So we just said, again, total energy has to include those dissipated forces, the energy internal. If we're just talking about mechanical energy, the sum of the potential and kinetic remains constant when there are no other forces. So once more, if there's no friction, which is what it means in a closed, isolated system. This means there's no other forces acting besides the object and gravity typically is what we're talking about almost in all cases. Yeah, the object and gravity, there's no other forces acting on it. Of course, again, we have a normal force if we're talking about surfaces. That doesn't necessarily matter in this case because the normal force doesn't do any work, so we don't care about it in this case. So what ends up happening here, and this was in the notes from yesterday. I really like this analogy of a savings account. In this system, if there's no other forces, the total mechanical energy is the total energy if there's nothing else going on. Yeah, if I just drop a ball, boom, no friction. If I push across a frictionless surface, no other forces, yes? What ends up happening is there's this kind of balancing act going on between potential energy and kinetic energy, yeah? So think of it as two savings accounts. This was the analogy from the notes yesterday. If I have two savings accounts, you guys might know this if you're taking finance with me next semester. I think I have one or two of you who are actually taking finance. Savings accounts, you don't spend money from. Yes, you can transfer money out of it, but you, like your debit card, you can't pull any money from your savings account unless you go to like an ATM and make a transfer. Yeah. If you're swiping your card at the grocery store, none of that money comes from your savings account. And in fact, it can't. You would have to go to an ATM, make a transfer, or go to a bank app or whatever. So say you have two savings accounts and you just transfer money kind of back and forth between those two savings accounts. The total money you have is not changing. We're not taking any money from the total of all of those savings accounts. But yes, the two are changing. I pull money over here, okay, now this is greater. I pull money over here, now this is greater over here. So as potential energy increases, kinetic needs to decrease, and then vice versa. If kinetic is increasing, potential is going to decrease, and in fact, at the same amount. So if potential energy increases by 10 joules, kinetic will decrease by 10 joules. This is, again, only the case when there's no non-conservative forces. If there are some non-conservative forces, that's going to impact things, and we'll talk about that at the end here. Now, this can be demonstrated with, this is the formula they tend to use. The sum of your initial kinetic and potential energies equals the sum of your final kinetic and potential energies. Now, more importantly, though, the sum at any 2 points, or any 3 points, or at all points, however you want to say about it, it's the same. So it's not just the beginning and the end is the same. The beginning and the middle is the same. A quarter of the way down and 3/4 of the way down is the same. At any 2 points, or again, at all the points, however you want to think about it, in an object's motion. And again, think typically we're talking about something being dropped, yeah? Or something that, again, will have potential energy. We are going to talk later about springs as well, and springs have potential energy. The sum is going to be the same at any point. It doesn't mean that, again, the kinetic energy is constant and the potential is constant. It just means that when I add them together, it will be the same throughout. We'll practice that more in class. Last thing we're going to do here, and then we're done. I know this was a lot of note taking. If you were in person, it was pretty easy. But if you're at home, maybe not so much. Now, we haven't talked about this necessarily just yet with potential energy in particular, and kinetic as well. But when we have different paths, so obviously if something is dropping, that's pretty straightforward. We can also still have situations where I'm going down at an angle or going down kind of zigzagged or whatever, yeah? A linear path, just straight down, versus a non-linear path. Or I should say an angled path even. Now, when friction and air resistance is not involved, so meaning there's no friction, there's no air resistance, what ends up happening is it does not, matter. It does not matter what path is taken. By the end of the path, of the motion, the kinetic energy and potential energy will actually stay the same. That's because, again, it's constant throughout when there's no friction, when there's no air resistance. If we're starting from the same height, if I'm starting from the same height, dropping straight down versus going this way, we're going to end up with the same potential and kinetic energies because there's no other forces involved impacting them. However, if there is friction or air resistance involved, it does matter what path is taken. And that's because even if I'm going straight down a slope versus kind of zigzagging. Yeah, if you've ever seen skiers, they kind of do this thing where they zigzag sometimes. More contact with the rough surface will change the kinetic and potential energies. So again, even if I'm going straight down versus zigzagging, yes, I'm starting from the same height. If you recall, potential energy is mass times gravity times height. But if there's friction involved, that is going to impact things because it's a non-conservative force. It's going to impact the velocity. It's going to impact the potential energy just a little bit. And so that will change things. So as an example, here's to wrap up. Say that Sally drops a ball straight down to the ground from a certain height h, and Bob rolls a ball down a frictionless incline that is raised to the same height. So this is what it's saying here. These are the pictures. Excuse me. Sally drops a ball straight down from a height of h. Bob rolls a ball down a frictionless incline that is raised to the same height h. Now again, yes, this path is going to be a shorter path than this path. Correct. But at any points along these paths, here to here, since this is frictionless, what do we think about their kinetic and potential energies at these points? They're going to be the same. They are the same throughout. And again, if this is a little confusing, we're going to try some practice problems in class to make it make a bit more sense. That's because, again, there's no other forces involved, yes, that are impacting our ball. They start at the same height. They drop at any of the same heights throughout. We're going to have the same kinetic and potential energies. Now we have a different situation here where Adam and Bobby are twins. They got the same weight, which is good because, again, potential energy is impacted by mass. Adam drops to the ground from a tree at height h. So here's Adam on a tree. That's my tree. Whoa, that's terrible. That's a tree. Here's Adam. He drops from height h. There's the branch. And Bobby is sliding down a slide, still from the same height h. Bobby goes down the slide. Whee! Here's Adam dropping down as well. They're starting at the same height. And I never really clarified this, but you guys need to understand, height means straight up from the ground. This is not referred to as the height, right? That length, that is the distance traveled. It's not the height. This is the height from the ground. Now, this slide is slightly sticky and plastic. If you ever down a slide before, think about it like that. How do their kinetic and potential energies compare now? Well, because there is friction involved, even though the potential energies are going to be the same, because potential energy is purely based on the height. The potential energies at the start of this will be the same. Potential energies are the same. That's because, again, that is just mgh. However, for kinetic energy, that's 1/2 mass times velocity squared. And that friction is going to impact their velocities. So the kinetic energies are going to end up being different throughout this travel. The kinetic energies are different because, once again, kinetic energy is 1/2 mass times volumes. Sorry, velocity, speed squared, friction is going to impact this. And so the kinetic energy is going to end up being a little bit different. Friction is going to cause some heat. And again, you may have felt that going down a slide before. That's why you get rug burn or slide burn. That's literally friction causing that heat and burning you, yeah? So some of the energy in this system is going to go into burning poor old Bobby and getting rug burn or slide burn, yeah? So some of the kinetic energy, even though he had all this potential, Bobby had so much potential for all of this energy, not all of it gets converted into kinetic. A little bit of it is going to get converted into heat because of friction. So once more, Adam and Bobby start with the same potential. They both are starting at the same height. They both have the same potential for all of this kinetic energy. But by the end of the slide, Bobby's kinetic will be less because some of that potential went into heat. So we are going to talk more about this in class. I know this was a lot. I know this is me just kind of talking at you and you copying a lot of stuff down. Like I said, we're going to go through some practice problems that really pick apart all of these notes and make it make a bit more sense.